there, science fans! Today we're diving into the exciting world of vectors. What are vectors, you ask? They're like arrows that point the way, but they're even cooler than that. Vectors are mathematical tools that help us understand and describe things that have both size and direction. Imagine you're sailing a boat. You need to know how fast your boat is going, right? That's speed. But you also need to know which way you're headed. That's direction. Vectors combine both of these things, magnitude, which is size, and direction, into one neat package. Vectors are like secret codes that unlock the mysteries of movement, forces, and all sorts of cool phenomena in the universe. So, buckle up, because we're about to embark on an adventure with arrows. Remember those treasure maps we all love? You know, the ones with the big X marking the spot? Well, guess what? Those maps use vectors. See, to find that buried treasure, you need to know more than just how far to go. You need to know which direction to go in. Imagine the map says walk 10 paces in which direction? North, south, east, west? Without knowing the direction, you'll be wandering around like a lost puppy. That's where vectors come in. A vector on our treasure map would tell us to walk 10 paces to the north. It would have a magnitude of 10 paces, that's how long our arrow would be, and it would point north, giving us the direction. Now we're talking. With vectors, we can follow those maps straight to the treasure. Vectors are everywhere in our daily lives. They are an essential part of how we understand and interact with the world around us. They're not just hanging out on treasure maps, you know. Vectors are present in many of our daily activities, often without us even realizing it. Let's take a look at some real-life examples of vectors in action, from sports to everyday tasks. Playing catch. When you throw a ball to your friend, you're using a vector. The ball's path is determined by the vector you create. The speed of your throw is the magnitude, and the direction you throw it in is, well, the direction. This combination of speed and direction is what makes the ball reach your friend. Flying a kite. The wind that pushes your kite up into the sky is a vector. The kite's movement is a result of the wind's vector. It has a magnitude, which is how strong the wind is blowing, and a direction, which is which way the wind is blowing. This vector determines how high and in which direction your kite flies. Driving a car, when you're behind the wheel, you're constantly using vectors. Every turn and acceleration involves vectors. The speed you're driving is the magnitude, and the direction you're steering is the direction. See? Vectors are everywhere. They help you navigate the road safely. They're like the unsung heroes of motion and forces, helping us understand how things move and interact with each other. Pretty cool, right? Vectors truly are fundamental to our understanding of the physical world. Now, you might be wondering, what's the big deal with vectors? Can't we just use regular numbers? Well, not always. That's because regular numbers, which we call scalars, only tell us about magnitude or size. They don't tell us anything about direction. Think about it this way, your weight is a scalar quantity. It tells you how heavy you are, but it doesn't tell you which way gravity is pulling you. Hint, it's down. Vectors, on the other hand, give us the full picture. They tell us both magnitude and direction, which is super important for understanding how things move and interact. So next time you need to describe something that has both size and direction, remember, vectors to the rescue. Section 5. Drawing vectors. From lines to arrows. Vectors are usually represented by arrows. Why arrows, you ask? Well, let's dive into that. Because arrows are awesome, that's why. Just kidding. Sort of. But seriously, there's more to it. Arrows are a great way to visualize vectors because they have a natural direction to them. This makes them intuitive and easy to understand. The length of the arrow represents the magnitude of the vector. This means how strong or intense the vector is. So a longer arrow means a bigger magnitude, and a shorter arrow means a smaller magnitude. It's a simple yet effective way to convey information. The direction the arrow points in represents, you guessed it, the direction of the vector. This is crucial for understanding where the vector is headed. It's like drawing a map to your friend's house. You need to show both the distance and the direction. You could just tell them how far away it is, but it's much more helpful to draw them a map with an arrow pointing in the right direction. This way, they won't get lost. Vectors are like those helpful arrows, showing us both magnitude and direction in one convenient package. They make complex concepts easier to grasp. Section 6. Vectors on a grid component form. We can also represent vectors using something called component form. Don't worry, it's not as scary as it sounds. Imagine a grid, like a giant piece of graph paper. We can use this grid to describe the direction of a vector. We do this by breaking the vector down into its horizontal and vertical components. The horizontal component tells us how far the vector moves to the right or left, and the vertical component tells us how far it moves up or down. We write the component form of a vector like this: horizontal component, vertical component. So, if a vector moves 3 units to the right and 2 units up, its component form would be 3, 2. It's like giving someone directions using blocks east and blocks north. Section 7, Vector Addition, Joining Forces. Just like we can add numbers, we can also add vectors. Vectors are quantities that have both magnitude and direction. It's like joining forces to create a supervector. When we combine vectors, we get a resultant vector that represents the total effect. To add vectors, we simply add their corresponding components. This means we add the horizontal parts together and the vertical parts together. Let's say we have 2 vectors, equals 2, 1, and equals 1, 3. These are their components. To find the sum of these vectors, plus, we add the horizontal components, 2 plus 1 equals 3, and the vertical components, 1 plus 3 equals 4. This gives us the new vector's components. So plus equals 3, 4. This is our resultant vector. Geometrically, we can visualize vector addition by placing the tail of the second vector at the head of the first vector. This method helps us see the direction and magnitude clearly. The sum of the vectors is then represented by the arrow that starts at the tail of the first vector and ends at the head of the second vector. This arrow is the resultant vector. It's like taking a detour on your way to your friend's house. The path changes, but you still reach your destination. Section 8. Scalar multiplication, stretching and shrinking vectors. We can also multiply vectors by scalars. Remember, scalars are just regular numbers. Multiplying a vector by a scalar changes the magnitude of the vector, but not its direction. For example, if we multiply the vector equals 2, 1 by the scalar 2, we get 2 equals 4, 2. We simply multiply each component of the vector by the scalar. Geometrically, scalar multiplication is like stretching or shrinking the vector. Multiplying by a positive scalar stretches the vector, while multiplying by a negative scalar shrinks it and reverses its direction. It's like using a zoom feature on a map. Section 9. Unit vectors, the direction superstars. Now let's talk about unit vectors. These guys are the direction superstars of the vector world. A unit vector is a special vector that has a magnitude of 1. Unit vectors are super useful because they allow us to isolate the direction of a vector. We can think of them as pointing in a particular direction without any stretching or shrinking. We usually represent unit vectors with a hat symbol on top of them, like this. The most common unit vectors are which points in the positive x direction and which points in the positive y direction. They're like the compass directions of the vector world. Section 10. Parallel vectors, same direction, different journeys. Sometimes we encounter vectors that have the same direction but different magnitudes. These vectors are called parallel vectors. They're like 2 cars traveling down the same road, but one car might be going faster than the other. We can tell if 2 vectors are parallel by looking at their components. If the components of one vector are proportional to the components of the other vector, then the vectors are parallel. For example, the vectors equals 2, 1, and equals 4, 2 are parallel because the components of are twice the components of. They're like 2 friends walking side by side, but one friend might be taking bigger steps. Section 11. Vectors in physics, forces, and motion. Vectors are especially important in physics. They help us understand how forces affect the motion of objects. For example, imagine you're pushing a box across the floor. The force you apply to the box is a vector because it has both magnitude, how hard you're pushing, and direction, which way you're pushing. By breaking down forces into their vector components, physicists can analyze complex systems and predict how objects will move under the influence of multiple forces. It's like being a detective, but instead of solving crimes, we're solving the mysteries of motion. So, there you have it, science fans. Vectors are powerful tools that help us understand the world around us. From treasure maps to forces in motion, vectors are everywhere. Keep exploring, and remember, science rules.